Hello everyone, welcome to our video. Today we will continue with linear algebra and the calculation of the determinant, and we will move on to the inverse of a matrix after this. So let's start. First we have a theorem that states if we have the n by n matrix A, and in order to have an inverse of this matrix A, the necessary and sufficient condition is that determinant of A is not equal to 0. Here is a quick example. Suppose we are given this matrix A, and here we have an unknown parameter x. So these two elements are given as x, and now we can check the condition, the determinant of this matrix A. And we can see that if we use the last row here in the calculation of the determinant, that will be more convenient for us because these two terms are 0. So we will only need to evaluate this 3 times. The remaining minor is, or the subset, let's say, sub matrix, let's say, is given by 1x, 1, 2. So that is here. This is our minor. And then the determinant of this is 1 times 2 minus x. So this is given here. And the necessary and sufficient condition we just mentioned says this cannot be equal to 0. So that means x is not equal to 2. And in this case, the inverse of A exists according to our theorem. We have some more properties and results about the determinants of matrices. Here is another one. Basically, if we have A and B, both of them are n by n matrices, then the determinant of A times B equals to the multiplication of determinant of A and determinant of B. Okay, and another remark here. Determinant of A is not equal to 0, and A times A inverse equals to identity matrix. Then determinant of A times A inverse equals to the determinant of the identity matrix. But we know that the determinant of identity is always equal to 1. So actually, from as a direct result of the above theorem, we can split this expression as the multiplication of these two determinants, but the right hand side here equals to 1. Because determinant of identity, for example, if we have identity matrix 1, 0, 0, 1, so this is also 1. It's just as an example 2 by 2. So determinant is, as you see, if we evaluate the determinant of this identity, that's equal to 1 times 1 minus 0, that is 1. As we can also check for larger n by n matrices, but it will always be equal to 1, not only for this 2 by 2 case. So determinant of the identity is always equal to 1. And therefore, we can say that determinant of the A inverse equals to 1 over determinant of A. So this is now a direct result of this theorem that is stated here. Now, here's an example. Suppose you are given this matrix A, and you are also given the determinant of A. Then, what is the determinant of A inverse? We have just seen right in the previous slide that the determinant of A inverse can be written as 1 over the determinant of A, which is going to be 1 over 320. Another example. Suppose we are given A times A transpose equals to A inverse times B. Now, the question is asking, write determinant of B in terms of the determinant of A. And we can easily do this. First of all, since I'm looking for the determinant of B, we can actually multiply both sides by the matrix A, and from the left we multiply both sides with the matrix A, and A times A inverse we will have identity, and the right hand side becomes just the matrix B. So it is equal to matrix B. And on the left hand side we have this guy. Now if we take the determinant of both sides, then this tells us we can apply now the last theorem and split these determinants one by one. But determinant of A transpose is also same as determinant of A, right? Therefore, this is the third power now. Okay, another example. A times B is given with this 3 by 3 matrix, and the determinant of A is also given as equals to 3. Then the question is asking what's the determinant of A inverse times B transpose? And remember, we know that we can actually write the determinant of this matrix as determinant of A times determinant of B, but this is already easy to evaluate relatively because you have 3, 0, 0. So if you evaluate the determinant for this matrix, you can use these, and these are 0, so we don't need to do anything about them. And we have basically the sub matrix, the minor is here, minus 1 times 5, minus 0 times 2, that is 0. So that's minus 5 times 3, that gives us minus 15. Now, since we already know the determinant of A times determinant of B, and we are also given that determinant of A equals to 3, then you can solve for this unknown determinant of B, right? Because this is equal to 3 now. So we obtain determinant of B equals to minus 5, as we see. And what about the determinant of A inverse times B transpose? As usual, we can separate them as a multiplication of two determinants. And remember, determinant of A inverse is 1 over the determinant of A, and determinant B transpose is same as determinant of B. Therefore, combining these together, this one is minus 5, and this determinant of A, we get 1 over 3. So 1 over 3 times minus 5, that's minus 5 over 3. This is what we are looking for. Another example, suppose we are given matrix A, and we are also given B inverse times B transpose equals to A times B. Then the question is asking find determinant of 3 times B. First of all, we can take the determinant of both sides. So that's determinant B inverse times B transpose equals to determinant of A times B. And then just use the theorem basically from this line and then separate these terms, okay? So we separate them. And we can see this is 1 over determinant of B, and this is determinant of B. So these two cancel and you get this 1, okay? This multiplication, we just cancel them, and that gives us 1 equals to the determinant of A times determinant B. And if you like, you can write determinant of B as 1 over determinant of A. That's equal to 1 over 6, because here you can calculate the determinant of A using the first column, and you will multiply this 2 with the minor. The minor is here. 1 times 3 minus 0, that is 3, times 2, that is 1 over that the determinant of A equals to 6. Okay, so determinant of B equals to 1 over 6. And what we are trying to do is we want to calculate determinant of 3 times b. But this is A and B are 3 by 3 matrix. So we can factor out this 3 from each column. So that gives us 3 times 3 to the third power times determinant of b. And just now, determinant of b we plug in as 1 over 6. So that gives us 9 over 2 as the final result for this expression, determinant of 3 times b. Another note, if we have an n by n matrix A, then the determinant of k times A, here k is a scalar, if we multiply the matrix A with a scalar, then this k gets out of the determinant as k to the power n. So as we have more number of rows or columns, then this power will, the nth power, that will increase proportionally. Here we have another, we are given a matrix B, and then if we take the scalar multiplication of this matrix with the number k, that means every element is multiplied by the same scalar k. And then the determinant of k times b equals to k cubed, because here we are talking about the 3 by 3 matrices. But if it is 4 by 4, then this will be k to the power 4. And you have the determinant of this matrix, which is b in this example, and that's the k cubed times determinant of b. Okay, let's stop here, and we will continue with the Cramer's rule to solve the system of linear equations. We will continue from here in the next video. Thank you.